Okay, there's that. I have the web page open, so I'll share that with you in just a second. Alrighty. So this morning I updated, by the way, the printable version of the syllabus. At least I thought I did. Um, it doesn't say that the date has changed. Maybe I forgot to change that. But when you click on it, it should say that it was updated this morning. That way you have a full record of what actually happened in the class in case you need to provide that for some future class or something like that. Let me see if it's the right date on this version of it. No. Okay. Well, it's not translating on here, but I swear I did. Anyway, I'll check on that after class. The other thing that I did is post what office hours are going to be next week. So the good news is that I'm finally done with class prep for the semester. So I have a little bit of extra time. And so I thought I'm just going to bombard you with office hours because no one is going to fail this class on my watch. That is my objective here. So every afternoon next week, I will have availability to sit on Zoom and you can log in and get help immediately with whatever you're working on. So Cassie is not available next week, which is why I'm taking over those shifts. So a couple hours every day, 2 hours, 3 hours, and it will be both of my classes I'm offering this to. So there may be a few more people than you're used to, but I wanted to make sure that everybody has access so that they can get all their stuff done. So how about that? Good. All right. If you're not available during these times, you can always email me. So if you send me a screenshot of your code or your output, I can help you troubleshoot what's going wrong, or let you know if you need to write additional statements in your code, that kind of thing. The other announcement, as I said over email, I'm offering you a deal with respect to course evaluations. So I know that this is a weird semester. I know that the quantitative numbers may not count, so to speak, in classes. I don't really care what the numbers are, but I do very much value your feedback. And given that we may be doing all the classes this way in the fall or for the foreseeable future in the worst case scenario, trying to figure out how to make it work based on your experience this semester is really important to me. So if I can get at least 15 out of the 17 of you to do a course evaluation, and that includes the standard questions as well as the extra questions that I added that are specific to aspects of the class, I will give everybody a point of extra credit. So I don't know which of you have completed evaluations. It tells me how many, and the system allows me to send reminders to people who haven't done it, but I don't see who those messages are going to. So you'll have to nag each other for cooperation on this if you'd like to make sure that we can hit the 15 benchmark. So that's my deal. All right. Questions, comments on any of that logistical stuff? We have a chat. Let me find my chat window. You are welcome. Do I know how many have done it already? Nope. I can check on that though. It's available to me in Maui. Also, if you have feedback for Cassie, one of the questions I think says, is there anything else you want me to know? Please go ahead and include that, and so I can pass that along to her if there's any things that you wanted to tell her as well. Anything else? Questions, comments? I'll give you an update on Thursday as to how many people have done it, and I believe it closes Saturday night. So it's either this Saturday or next Saturday. I think it's this Saturday. So, all right. Then in that case, you should be working on homework 5 at this point. We have answers to go over for the quiz, so I'll start with that. We have number 6. Let me pull this up. One of the questions is somewhat of a review. The other 2 are new to this unit. I had a look at the answers already, and it looks like everything went reasonably well. I just want to make sure that I can clarify what I was thinking the answers would be in these cases. So number 1 here, in what situations, what types of predictors and what types of relationships would a Pearson correlation be sufficient to capture a bivariate relationship, and in what situations would it be insufficient when you have to fit a model instead? What it boils down to, A Pearson correlation captures a linear relationship between a quantitative predictor and a quantitative outcome. It cannot capture nonlinear relationships, so such as quadratic curves or piecewise slopes, when there's a different effect of a predictor at different sections of the predictor. For those situations, you would need a model instead to look at the bivariate association between a quantitative variable and a quantitative outcome if the association has that nonlinear form. Another situation when you have categorical predictors. So if you want to look at the association between, say, a nominal or ordinal predictor and a quantitative outcome, that needs to be done in a model because you need to have multiple slopes. So if I had 4 categories in a variable, I would need 3 slopes, for instance. Putting those all together provides an index of the strength of the association as the model R-square. And another situation, number 3 on the list, would be if you're interested in knowing about a relationship between 2 variables after controlling for a third or more variables. So what is the impact of nicotine on newborn deficits after controlling for socioeconomic status? Something like that. If you want to be able to rule out common causes, so to speak, that has to be done in a modeling framework. So 3 reasons, just to recap real quick: to capture nonlinear relationships among quantitative predictors, to capture relationships of grouping variables, nominal or ordinal, with a quantitative predictor, as well as to look at a relationship after controlling for some other variable. Those would be the 3 reasons you would turn to a modeling approach as opposed to just a bivariate association. Okay, questions on that point? Draws back. I'm watching the chat window this time. I swear I'll answer if you actually ask. Okay, no questions? Okay, carry on. Number 2. In what situations would you expect the unique effect of a predictor to be different than the bivariate effect? I think all of you pretty much hit the nail on the head for this. It's when you have more than one predictor in your model. More specifically than that, when you have predictors in your model that have some sort of association among them. So if a predictor is correlated with another predictor, then we have to talk about what the relationship would be that's unique to the predictor. And the common part, so to speak, the point of overlap between the predictors, neither predictor would get credit for that specifically. So we had a Venn diagram in lecture 5 that described that, right? Where we have this predictor has a unique effect, this predictor's unique effect, and then the common part between them. The common part does go into R-square, so the model gets credit for it, so to speak, but each individual predictor doesn't. So whenever predictors are related to each other, their effects, their slopes, are going to be different depending on which predictors are in the model. So correlated predictors is the shorthand for that. So questions on that one? Yellow thumbs up. Thank you, Cheryl. 2 thumbs up from Jeff. Oh, that must have been a really good answer. Yes, thank you, yellow thumbs. All right, last one then. A repeat, because this is one that's important. So things to walk out of this class with. What is the relationship between effect size, statistical significance of that effect size against a null hypothesis of 0, and sample size? So when we say that we have a slope that's significant, it could mean one of 2 things. There's a strong association, or we've got a lot of people. Effect size gives you the strength of the association in a metric that is readily identifiable. So it's a way to take a slope, which is always specific to the units of x and the units of y, and translate it into something where the numbers have inherent meaning. So for instance, the R effect size, no association is 0, and a perfect association, either positive would be +1 or negative association would be -1. So we can take an unstandardized slope that's something like, units of education and units of income, for instance, in the example we were working with, and translate that into what would the slope be if the predictors and outcomes were z-scored, where they were put on the same scale. Then we have an association in an inherently meaningful metric. Whether or not that association is significant is a different question. If you have a larger sample, it will be easier and easier to declare very small effects to be significant, to be unexpected to have happened if the null hypothesis of no effect were true. So the more people you have, the greater chance you have of finding something to be significant. In other words, the more people you have, the more power you have. So you can end up with significant results that actually are trivially sized associations if you have a very large sample. The converse of that, if you have a very small sample, you can have very large associations be non-significant because there's just too much noise relative to signal when you don't have a lot of people. So to be fair in your reporting, you would always want to report an effect size for whatever association you're talking about, as well as a p-value that gives you the level of significance. And your method section would have already explained how many people you have, and so then your reader would have all of the information that you need. And we'll get more examples of this today in example 5. All right, questions or comments on that? Nope. Okay. Then with that, formative assessments are complete for the semester. Hooray. So I will shut this down. Everybody should now have your 12 points. I updated the points this morning before 9 o'clock, so if you've done it since then, it's not included in the grade total, but I'll take another swing at it and send out reminders to anyone who still needs to do it. That way you can get your points. All right. Where do I want to start? Should we go back over the idea of models with more than one predictor? A little review from last week. Would that be good? Yeah, we'll start there. We'll start at the beginning then. Slide number 1. All right. So stuff that we've already talked about. Prior to this example, even though we had multiple slopes in the same model to describe either a nonlinear effect or the effect of a grouping variable as a predictor, those multiple slopes work together to describe the effect of one concept. So for instance, if I have a group, it may take 3 slopes to delineate amongst 4 groups, but it's like one idea. A group is a predictor. Likewise, if I want to know if age is associated with income in example 4, it took 2 slopes to describe the effect of age, a linear effect and a quadratic effect. So they work together to describe the effect of one variable conceptually as a predictor. Where we're headed now is combining multiple predictors into the same model. And what we would want to know is how well do they work together to describe the association between the predicted outcome for each person and the real one. So talking about R square there, R square is the correlation between the predicted outcome and the real one. And we would also want to know individually how well each predictor contributes to that R square. So we want to know sort of at a predictor by predictor level as well as a global level. And in this sort of situation, you can think about it as if we add things to the model, do they help? And so this is the new concept that we haven't talked about yet, is how to test changes in R square. So that's where we are headed. So we talked about this last time. This is all review, so we can skip a little bit of that. So the language changes when you're talking about the effect of a predictor amongst other predictors. It goes from bivariate to unique. and it's this idea of trying to control for what's in common. So we have the Pearson family here, of course, from the cast of This Is Us, not to be confused with the Pearson correlation or the Pearson chi-square or the Pearson Testing Company, which is yet another set of Pearsons. Pearson is a very popular name. But I had an example of them trying to clean the house and then trying to figure out who gets credit for how many rooms. And the bottom line is that even though each person's contributions make the overall house cleaner, if I want to try and figure out how many Nintendo games I'm going to hand out, I can't allow overlap. I can only give one reward per unique room cleaned. So that idea is commonly described with this sort of diagram here. I think of it as a Venn diagram. It's called a Ballantine or Ballantine. I'm not sure which pronunciation. But the idea is that of all of the ways that this outcome Y is predicted, we're trying to carve up those sources of variability in the prediction and assign them to different causes. So in this picture, the part that's A is the part that X1 contributes to the model as its association with Y uniquely. B is the part that X2 would contribute its association with Y uniquely. And C is the part that's in common. So the common part means that this is information that is shared across X1 and X2. So it contributes to the total R square, the total level of prediction in the model, but no predictor should get credit for it uniquely because we wouldn't know which one to give it to. So that idea of subtracting out the common part is what shows up through all of these equations here. I don't expect you to memorize them, so I'm just going to skip over them for right now. The idea of effect size then has to be analogous to this. So if you only had one predictor, a standardized slope for that predictor would be the same as its Pearson correlation. In this case, we have to change the language to go with the idea that the slope conveys a unique effect rather than a bivariate effect. And so the type of effect size that goes with that is what's known as a semi-partial correlation. It's the extent of the correlation between the predictor and the outcome after controlling the predictor for the other predictors. So this is a statistic that shows up on your output if you ask for it. Just as R, if you have a Pearson correlation, if you square it, becomes R square. If you square this, the semi-partial correlation squared is how much of the model's R square is directly attributable to that predictor. So it's how important that predictor is in a relative sense is conveyed by the semi-partial correlation. So in terms of reporting effect sizes for models that have more than one predictor, you can still ask for standardized slopes. You can also ask for semi-partial correlations. They're in different metrics, but they're going to converge onto the same idea. How much of the model prediction of the outcome is attributable to that predictor uniquely? And is it important? Okay, R square gets the common part. That's the point of this slide. So the interpretation then changes. The intercept is going to be when both predictors are 0. The slope for the first predictor is the unique effect after controlling for the other predictors. And all of those are scale dependent. Standard errors are going to reflect how much of the variability in the predictor is unique versus shared. So that's another source that goes in here. That means that standard errors are going to be higher whenever it's harder to figure out how much unique variance a predictor has. So if you have two predictors that are really highly related, their standard errors in the model would be higher as a consequence of the fact that there's less unique information in each of them. There's more about that later, but I'll skip that for now. So we can get these single slope effect sizes as a standardized slope or as a squared semi-partial correlation. But we have to do something different if we're adding more than one predictor at the same time. So let me open up my friend Excel here to type into to show you what I'm talking about. So I'm just going to make some shit up off the top of my head. Is that cool with you guys? That's cool? Okay. Well, I mean, like you're going to argue, right? I'm just going to mute all of you. I'm like the overlord here of Zoom. But let's say that we have a model predicting y, and here's the R-square value for the model. So if I have an empty model, right, I'll just list the predictors here. Y equals just the intercept. So this is, I'll put the word in there, empty model. What's my R-square going to be? If I don't have any predictors, the only thing in the model is the intercept, meaning that my best guess for everyone's score is just the grand mean, and that's it. In this case, what's my R-square going to be? Yes, 0. Very good. If I add something, let's say that y equals intercept plus a slope for the predictor A. Let's say now that the predictor A got my R-square up to 10%. How do I know if the difference in R-square is significant? Well, the difference between the models is the one slope that I have for predictor A. So if that individual slope has a significant t-test statistic, that's all the information I need. So I can say t for slope, or t squared equals f for the model. With one slope, those two tell me exactly the same thing. Okay, with me so far? All right, let's say that I add a predictor. Another slope, a, stop it, plus b. Let's say that my R-square goes up to 0.15. Going to add a column here. And that column is going to be R-square diff. So if I go from 0 to 10%, that's a change of 10%. If I go from 10% to 15%, that's a change of 5%. How do I know? Will I share the document after class? I would love to. How do I know if that change in R-square of 5% is significant? Now, this is a question for you guys, not a rhetorical one. I've added one new slope for the effect of b to the model. My R-square went from 0.10, or 0.10, 10% to 15%. That's a change of 5%. How do I know if that change of 5% is significant? F? That would be, it would either be, in this case, t for the b slope. Because I've only added one term to the model, if the t statistic for that one new term is significant, that means the change in R-square is significant. There's a one-to-one correspondence there. The F for the model would be the test of whether this R-square is significant, the R-square that has both of them. So that alone wouldn't tell me if the difference between these models is significant. Let me add another new column here. Significant R-square. I'm going to add that column. That is the same thing. Hey, stop that. This and this are the same. There. We'll wrap text so we can see that a little better. Freeze panes. All right. So in this first case right here, focusing on this, because the change in the R-square is relative to 0, and I've only added one predictor, the t-test statistic for that one predictor slope tells me the same thing as the f-test statistic for the R-square for the model. That one slope is the model. It's responsible for all the R-square. If I compare these two lines, there's two different questions that I might want to know. Is the overall R-square for the model significant? On the whole, does the model work, so to speak, in predicting the outcome? The F for the model would tell me whether that 15% is different than 0. The F for the model, though, is lumping together A and B because that's what's in the model. So in order to figure out whether or not the change in R-square, what A did all by itself was 10%. By adding B, I picked up another 5%. To know if that change is significant, I just need to look at the t for the new slope. If the new thing that I added to the model has a significant effect, then the change in R-square resulting from that new thing is significant too. One-to-one correspondence. Okay. With me so far? Okay. Now here's a trickier one. Y equals my intercept plus A plus B. And let's say, for example, like in homework 5, off the top of my head, that I need to add a grouping variable that has 3 groups. So that's going to take 2 slopes to make that work. So I'm going to add C1 and C2 at the same time because that's what it takes to fully capture the effect of, say, C for my categories. Let's say that my R-square goes up to 0.27. That means the change in R-square is 0.12. So this is the new thing that you guys don't know how to do yet. The last new thing. How do I know if the R-square for the model, the 20.27, is different than 0? Same way I knew it from before, F for the model. Over here is the tricky part. How do I know if the change in R-square, the extra 12% that my model picked up, is significant, given that I added 2 things to it at the same time? In this case, it's not sufficient to look at either of their t-values because that doesn't tell the story. The 2 slopes that I added to differentiate among the 3 groups, those in turn predict another difference as a linear combination. So there's 3 possible differences. I only need 2 slopes to get all of them. If I had 4 groups, there'd be 6 possible differences. I'd only need 3 slopes to get all of them. So I have to find some way of lumping together C1 and C2 to test that contribution as a unit, as a lump, so to speak. So I need an F-test because F is what you get whenever you lump together more than one slope with another one. Nope. This is the new thing that you don't know how to do yet. But it's super easy. I promise, I promise. Here's how we do something like that. I'm going to hide these ones so that I have got more space to type. So this F-test for the model, this has been given to you this whole time. You didn't have to ask for it special. If you had wanted to ask for it special, here's how we would do it. In SAS, it's a statement called contrast. In Stata, it's a statement called test. And just like estimate statements happen within the model in SAS and lincoms happen right next to the model, these do too. So what it would look like in SAS to do a contrast statement, I'll do that one first, to get the F value for the model. What it's doing for you behind the scenes is that you would type each predictor, slope, separated by a comma. Hang on, I'm going to run out of real estate here. There we go. Like that. C1, C2. With the semicolon at the end, of course. Nope, forgot my ones, excuse me. Ones go after each. There. Now I have 2 ones after each. This is why I don't do live demos very frequently. There we go. So that's lumping together all 4 slopes to get a test of whether or not they work together to create a significant R-square. In Stata, the test statement looks like this. You put each term in parentheses. So it would be like C dot A and set it equal to 0. No commas. C dot B equals 0. C dot C1 equals 0. C dot C2 equals 0. So it's a little more explicit the way that the code looks in Stata, but what you are asking it to do is simultaneously test whether all 4 slopes are 0. That is how you know if you have a significant R-square for your model. R-square change then. By the same logic, what we want to test is the joint contribution of the new slopes. So the way that that would work, I'll type down here, R-square change is what we're looking at. We would remove the terms that were already there and just leave the new ones, C1 and C2. Likewise in Stata, we would remove the ones that were already there and just have the 2. So this is how you can ask whether new predictors as a set contribute to the model R-square. So whether or not they add anything, so to speak. And it takes into account how related they are together in doing this, which is why it's different than just looking at the t-test that goes with each of them. So this is the same thing as what other people would call hierarchical regression, this idea. You don't have to fit all the models separately to know what the contribution is of any set of predictors. I'm having you do that for practice in example 5, but in reality, I could have just asked you to go straight to the last model and write these kinds of statements to determine what the contribution is of each set of predictors. So in homework 5, I'm asking you to lump together both types of GRE scores. This is how you would test their contribution to the change in R-square, as well as the difference between people who fear statistics a little bit, moderate, or severely. Again, another complete hypothetical, right? So this is the last new concept in terms of code. It's what's known as a multivariate wald test. So F is used anytime you're testing more than one slope. Special cases of this include the R-square for the model test, so to speak, that lumps together all the model slopes, as well as tests for subsets like this. So I'll pause for a moment. How are we doing? Okay. And one nice thing about this in SAS, at least for contrast, is that it will also provide the semi-partial R-square that goes with the joint contribution. So you can get an effect size that corresponds to the F-test statistic. So again, effect size and not just significance. All right. Questions? Do you want to go through example 5? Yes? Okay. I have it up right here. So this is data from my book, as we talked about last time. I'm happy I've not gotten a bill for someone returning my book. I remember that story. I had to tell my husband about it. Like, it could be worse. I just looked at my royalty statement, and I'm happy to say I've sold 1,870 copies. Not exactly like bestseller, New York Times bestseller list, but that means like somebody found it useful, and therefore my 5 years of doing this was not a waste. So, yay for that. But this is the data from Chapter 2. So we are going to be predicting a cognition outcome. That's a measure of crystallized intelligence in a sample of fictitious older adults. There's 550 of them from their chronological age, which is going to be centered at 85. Their grip strength in pounds per square inch, which is going to be centered near the sample mean of 9, and their category as to what their dementia status is, where the most prominent group is that there's no dementia diagnosis. There's one where within the span of this longitudinal study, they're going to be diagnosed. We just don't, they're not at baseline. And then there's a group of people who already have a diagnosis, and they are the smallest group of the three. So this is based on real data, but it's in fictitious data. That way I could put it on the web. So this coding scheme that I've highlighted right here is your traditional dummy coding scheme, where it's the first group versus each of the others. In homework 5, I asked you to do something a little different. So you can use this coding scheme, but then some of your answers would be linear combinations, just to give you a heads up on that. So do you remember why I would want to center my my quantitative predictors at these numbers? This is SAS, yes, thank you. If I just entered age in the model without centering it, so that 0 is in the model, correct. So if I entered age into the model as a predictor without centering it, who would I be predicting cognition for? What kind of person? Uh, a newborn. I would be predicting cognition at age 0, right? That's what my intercept would mean. Now that's not wrong, but it's very weird. So given that I'm working with fictitious older adults, I centered it near the mean of age at the beginning here, which is 85, and did the same thing for grip strength. And I don't have to worry about 0 within dementia group because my coding scheme set it up so that what 0 means is that you're in the no dementia group, and what 1 means in each of these variables is in contrast to either the current group or the future group. Now here's another question. This dem group variable that's 1, 2, 3, are those numbers? No. It's arguably ordinal, but they're not numbers. What would SAS or Stata do if I put in dem group as a predictor? Would it run it? Yep. Would it give me garbage? Yeah, yes. Because it doesn't know they're not numbers. It would be happy to draw a line, a slope that fits from group 1 to 2 to 3, even though that would make no sense. So this sort of preliminary work in coding up predictor variables is really important to make sure that your model results actually make sense. It's not something that is obvious or intuitive, but if otherwise, the parameters that you end up with may not be as useful. All right, then we have Stata code to do the same thing, centering continuous predictors, quantitative predictors, and coding up my groups and adding labels for everybody. All right. Questions on the setup for the story here? Nope. So this handout has way more stuff in it than you need for your last homework. But I wanted to give you was an example of like if you were doing this in life, what are the steps that you would follow? And the first thing that I would always do is to look at descriptive statistics for the variables that I'm going to be working with. The primary reason to do this is to make sure they're not wrong. So for instance, when people have missing data in a data set, sometimes they indicate that by a particular numeric code. A common one is actually minus 99. So rather than leaving it blank, people might put in a minus 99. And the reason for that is because that's unlikely to be a real value in a data set since it's a negative number. And if you don't import your data correctly into a program that understands that's a missing data code, it might treat it as real data. So looking at descriptive statistics just to make sure that the minimum and the maximum are possible values, right? Just data accuracy verification is important. The other reason would be to get a sense of how to center your predictors. What mean or what value would make sense to use as a centering constant. So here are the descriptive statistics for the variables we're working with. It's from procmeans in SAS, and it's from summarize in Stata. So we have cognition ranges from 0 to 44. That's my outcome. Note that I'm not going to center my outcome. That's usually not done. I will center my predictor age. I'm centering it near the mean at 85. I picked 9 for grip strength. And gender is another variable that's in the story. That's coded so that men are 0 and women are 1. And so this proportion right here, it means that 59% of the sample are women. They're the one group. I also got a cross tabulation of the two categorical predictors that we're going to be working with, gender and dementia group. And so this is ProcFreq that gives me this cross tabulation in SAS or tabulate in Stata. And this is useful to know to make sure that you don't have any empty categories. So to make sure that all possible combinations of people exist. Otherwise, what you have to do is going to be different in terms of fitting those predictor variables. If you run into that situation in life, I'd be happy to tell you more about it, but I made it so that that's not going to be a thing for you here. So most of the people are in the non-dementia category, that's number 1, and many fewer people are in the other ones. And then some pictures. So these are histograms. I have age in years as one of my predictors. I have grip strength in pounds as another over here, and then the cognition outcome. Just as an aside, in these models, one of the things that we have to assume to believe our results is that the outcome residuals, the E's that are left over, are normally distributed. So I included here, this is sort of giving away the end of the story before we get there, that this is what the residuals are going to look like. They're relatively more normally distributed than the cognition outcome. So you don't know what they're going to look like until you're done fitting the model. That's why it doesn't necessarily make sense to transform data or do any of that kind of stuff ahead of time because residuals are always model specific. Another thing to do then, so this is sort of walking you through everything that we've done this semester. Getting descriptive information for our variables, so univariate statistics, measures of central tendency, dispersion. Bivariate, So here is a Pearson correlation matrix between cognition, the outcome, age, grip strength, and gender. I'm not able to do that because for dementia group because that's a 3-category variable and I have to be able to explain to it that those aren't numbers. And so I didn't include that variable here. But the first column, we highlight these ones right here. This is telling me whether or not each predictor is related bivariately with the outcome. So what I have highlighted here are the Pearson correlation values for each combination. So age, for instance, is correlated negative 0.17 with the outcome cognition. Grip strength is correlated 0.24, and gender is correlated minus 0.24. So direction matters in terms of what type of association it is, but in terms of the significance, it doesn't matter. So let's say we'll call it minus 0.2. That means as age goes up, you can do hand signals on this one. A negative correlation of 0.2 means as age goes up, cognition goes down. Yes, thumbs down. Older people did not do as well on this measure of crystallized intelligence. Now, this correlation of minus 0.17, is that big? Is that a lot? Not really. I mean, it's not zero, but it's closer to zero than to -1, certainly. Is it significant? How do I know? Where do I look? Yes, this number right underneath it. That's my p-value. That's the probability of observing a correlation of minus 0.17 if the true correlation were 0. So even though this correlation value, this effect size, is not that big, it's very unexpected. How do I reconcile those two things? It's a smallish effect, yet it's still significant. Why? Because of the N, yes. I've got 550 people. Fake people are very cheap to sample from, as it turns out. You just ask your computer to get more. They're infinite. So significance is always a function of sample size and effect size. You got to know both to figure out, to have a good sense of what you're actually looking at. Same tendency here, but in the opposite direction. So this is also a significant correlation, but it's positive 0.24. So as grip goes up, cognition goes up. Yes, positive. Stronger people are smarter. So instead of being here, we should all head to the gym. I'm halfway there because I'm dressed in a workout clothes. It's the new normal, my homeschool uniform. All right. A negative correlation for gender. Now that's kind of weird, right? Because gender is not a number. But because it's treated as a binary variable in this instance, it actually is okay to do this. So the same language as x goes up, y goes up or down, you have to put yourself into the situation of what does it mean for x to go up in a binary variable. In this case, it means you are a woman, because the way the variable is coded, 0 are men and 1 are women. So if you are a woman, cognition is lower or higher than men? What do you think? Yes, that a little overly enthusiastic there, Jacob, but yes, they're lower in this case, significantly so. So if all I wanted to know is whether or not there was a relationship between cognition and each of these three variables in turn, I'm done. This chart tells me that. But what's not in here? Well, what kind of relationship are these two Pearson's correlations capturing? This is another hand gesture you can use. What's the form of the relationship that's assumed here between my quantitative variables? Yeah, linear. hmm Is it possible that um, the effect of age sort of levels off at some point? Or is it possible it gets even worse? Like there's a bigger difference between a 96-year-old and 97-year-old than there would be between an 86-year-old and 87-year-old? Possibly. I don't know. So if the association between these things is nonlinear, those two numbers are insufficient. Dementia group's not in this table because there's no way to get a correlation for something that's not a number in one value with an outcome. These three numbers are bivariate effects, just each variable paired with the outcome. Is there anything in this table that tells me whether or not the unique effects of these variables are going to be different? Trick question. Actually, there is. There's only one situation in which the unique effects are going to be the same as the bivariate effects when they're not related. So said differently, are my predictors related to each other? That's in here too. These last three correlations that we haven't talked about yet. There's a negative relationship between age and grip strength. Older people are weaker. As age goes up, grip goes down. So part of the association between age and cognition is going to be captured by putting grip strength in instead, because age and grip strength are related to each other. Does strength still matter after controlling for age? Does age still matter after controlling for strength? Meh. That's the part I don't know yet. I got to make them fight it out within the same model. Age and gender are unrelated in this case, so this is the only correlation that's non-significant. Correlation is 0.05. The p-value that goes with it is 0.29. So what that means is that if the true association between age and gender were 0, we would get a correlation of 0.05 around 30% of the time. So well within expected fluctuation, not significant, in the middle of the curve. Also, as one might expect, grip strength is higher in men than women. And I know that because there's a negative relationship, meaning as in women, grip strength goes down. So in practice, reporting this sort of correlation table whenever you do general linear models is standard. That way you can describe the relationships among your predictors as well as the bivariate associations of your predictors with your outcome. All right. Questions on any of that? All right, so what I did next then, fit an empty model. This is also, I think, did I ask for an empty model? Those of you who started homework 5, did I do that? Okay, good. All right, so here we go. So an empty model has no predictors in it. In terms of the code, cognition is the outcome. So that's what goes first after regress and stata down here. And there's no predictors. The predictors would normally go right here or before the comma in stata. So what this empty model is going to give me is the baseline. How much variability in cognition is there to be predicted? To find that, it's right here. Mean square error, or mean square residual in stata. That's my residual variance. In an empty model that has no predictors, that's all the variance there is in cognition. That's like R square of 0. See? R square of 0. That's how much variance there is. So this is another hand gesture question, okay? As I add predictors, what should happen to the residual variance number? This 120, should it go up or down as I add predictors? I see one vote for down. I'm watching the chat window too, so the black box folks can participate as well. What should happen to this number, residual variance, labeled as mean square error here, the 120? As I add predictors to the model, should it go up or should it go down? Jacob votes up, Carly votes down. Can I get a tiebreaker? Oh, got a few more down votes. A few more down votes. I got another up. This is tricky. This is why I'm asking you this, right? Because the two numbers that are highlighted here are directly opposite in what they're supposed to do. So residual variance is all the differences of each person's score, the real one, from what's predicted by the model. At this point, what's predicted by the model is just the mean for everybody. So as you add predictors, you refine the prediction. The residual variance is supposed to go down. So the 120 is going to become 110 and 100 and it's going to go down. But what that means then, R square is the proportion that it went down by. I'll say that again. R square is the proportion by which the residual variance went down. So as you add predictors, R square goes up. Yes, they're opposite. Yes, or disco, one of the two. No? I'm trying. So at this point, 120 is as much variance as there is in this outcome. That's all of it. We don't know anything about these people, why their cognition is what it is. That's all the information that we have, individual differences, so to speak. R square 0. Insert disco music, yes. I'm staying alive. Ah, 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 ah. Yeah, there we go. You're welcome. Now it's going to be in your heads the rest of the day. We're all staying alive right now. That's really like our only goal each day, right? Just to get through the day, stay alive, not kill anyone, that kind of thing. This is the quarantine lifestyle. So I'm going to add something to my model. I'm going to add age. Note in the equation here, I've indicated the centering. So age has been centered at 85. I have added some extra stuff. So SAS folks, this part here has more stuff in it. I've added the word effect size and SS3, which stands for sums of squares of the third type. This is the kind that we want. It cuts down on the amount of extra output that you have if you list that. So there's going to be some extra information here relative to what you're used to seeing. So in looking at the model results here, my one slope has taken that residual variance of 120 and sent it down to 117. The proportion by which the residual variance was reduced is right here. My R-square is 3%. Is that significant? Go ahead. No, R-square can't go down. It can't. It's in squared units. The worst it can do is stay the same. But I've got a 3% reduction. Is that good? Is that notable? I can look two places to find that out. Because the only thing that's in my model is a single linear slope for age, the F value for my R-square of 3%, which is significant, is the same thing as the T value for that slope squared. 4 squared, F of 16. Yep, and because those are significant, P less than 0.001, or 001 in this case, then yeah, that 3% is significant. There's an extra piece of output here. This is not something I'm asking you for on your homework, by the way, because it's something that the programs do differently. But your semi-partial, it's labeled as eta square. That's your squared semi-partial correlation. Because there's only one slope in the model, that is your R-square. In models that have more than one slope, it will be the proportion, it'll be how much of the R-square is attributable, how much of the amount of the R-square is attributable to each predictor. So my regression slope is right here. So for every year older, cognition goes down by 0.5 point. That's what the model says, significantly. I saved the results from SAS to make effect sizes with in D units, and I added that to the list here, as well as R units. So this is after making SAS do that extra math. My output has 2 new columns in it, a D, which is a standardized mean difference unit, which doesn't make as much sense here, or an R, and that is exactly the same thing as the Pearson's correlation. So this model doesn't tell us anything new relative to the Pearson correlation. It's giving us the same linear relationship between age and cognition. Here's something new. Testing whether or not the relationship between age and cognition is linear, or should it be nonlinear? So I'm adding a quadratic effect. You guys know how to do that. It's the original variable with an asterisk in itself in SAS, or in Stata, hashtag instead, #, to link those together. Now in this case, my model is testing the 2 slopes simultaneously. So is the overall R-square significant? The R-square is right about where it was before. Didn't really move. The 2 slopes together result in an F-test statistic of 8. So note that before, when we just had age, it was 16. Now it's cut in half. Because it's trying to give you the contribution per slope as an average. And one of my slopes is dragging down the other. More specifically, the effect of quadratic age. The slope estimate of 0.017 has a p-value that goes with it of 0.58. So it looks like the quadratic slope doesn't need to be there. This R-square is 0.0295. Without the quadratic term, it was 0.0291. I know that those are not different significantly because the new term that I added to the model is not significant. So that's the second row in the Excel table. Question from the audience. Does the R-square give you the significance to answer the question in the homework, or is it the p-value? P-value is always significance. R-square is effect size. So this is an instance in which, because I added one thing to the model, the change in R-square from adding that one thing has its significance tested as the slope for the new one term. So the quadratic in this case, for instance. So I don't have to do anything extra to know that. Because the new slope is not significant, wrong line here, excuse me. Because the new slope is not significant, the change in the R-square is not significant. One-to-one correspondence. Okay. How are we doing? You still with me? Doing so-so? So relative to my Excel table thing here, we were just talking about, this is an example of these two. It is hard to grab, I agree. If you add one slope to the model, the significance of that slope is the same thing as the significance of the R-square. F goes with R-square, T goes with the slope, but it's the same. T squared is F. If I add a second predictor, the F test for the R-square is lumping those two predictors together to find that out. But to figure out whether the change in R-square relative to the one predictor model is significant in the two predictor model, all I have to do is look at the p-value for the new slope, because I added one new term. If that one new term is significant, that means the R-square change is significant. They're, again, one-to-one correspondence. This is the new one in your homework. We haven't gotten there yet, but you will have to do something different to get a change in R-square test when you add more than one predictor at the same time. That's the new thing. So we haven't seen an example of that yet here. All right. Okay. Clarification, questions? I think. So same thing with grip. If I put grip in the model all by itself, so this is not including age anymore, just starting over, I can look at grip strength, the p-value for the slope that goes with that. That tells me the same thing as the F value for the model because the model only has one slope. If I add quadratic grip strength to see if there's a nonlinear relationship, now the F value for the model is lumping those two together, linear and quadratic combined, to know if the new slope created a significant improvement in R-square, increase in R-square, decrease in residual variance. I just have to look at that new term. And p-value right here, 0.67, not significant. So the increase in R-square from adding quadratic grip strength or the decrease in residual variance, not significant. We don't need it. Binary gender, that's not going to tell us anything different than the Pearson correlation did, but it will give us the actual difference in test scores between the two groups. So this is exactly the same idea as in homework 3, when you just have one binary predictor. If you have two groups, it only takes one slope to differentiate them. So the test of the model is the same thing as the test of that one slope. And the standardized slope for that one slope will be the same thing as the Pearson's correlation. Then the dementia group one. That one is trickier. So we'll do that one next time. So what I'm doing in this set of models here is looking at each predictor one by one to try to figure out how to best describe its association with the outcome. For quantitative variables, you would want to try and determine whether or not their effect is solely linear or whether there's some potential nonlinearity to that. Piecewise models may make sense in some circumstances. They didn't here because there's no like hard and fast cutoffs that would make sense to use as demarcations of slopes. For grouping variables, you would want to look at differences between groups and see which of those are necessary to be able to characterize the way the means differ in the model. So I want to know for each variable how to best describe it bivariately before jumping into a model that has all of them at the same time. We'll get to do that final step next time. All right. Questions, thoughts? So if you wanted to, you should be able to do the very vast majority of your last homework. It's adding one predictor at a time for the first section, empty model, one predictor, add two predictors, add grouping variables. There are a couple of questions about f-tests for the changes in our square that if you can extrapolate from this made-up example, then you should be able to do them. Otherwise, we'll talk about those last remaining questions on Thursday, our very last class. All right. Anything else before we adjourn? No? Okay. Then office hours at 3:15 if you need me. Otherwise, I shall see you guys on Thursday. Stay safe. Enjoy the Bee Gees. Disco lives on. All right, bye guys.